Hello friends, welcome to Truth of Physics. Previously, I have made a video on the concept of method of images. In that video, I have cleared the concepts and what is the method of images. I have discussed all about the concept, okay, in that video. Now in today's video, I will discuss some problems on the method of images, that how can you apply this method to any problem. Okay, suppose we have given a charge, we have given suppose two charges. One is 2q and another is suppose minus q, okay, near a conducting infinite plane which is grounded. Okay, now the distances are given, like this is the d distance and this is at 2d distance. Now we have to find the electric field at any point in the upper region. How can we do that? Okay, so for that we have to just make the similar charges in the below plane. Okay, that means we have to just forget this plane, this conducting plane, and we have to just image these charges. Like we have a mirror in this plane, we have to think this plane as a mirror and the images formed. Okay, that means here is the image of minus q and the similar charge but of negative sign, that is the opposite sign. That means here is q and at distance d and at distance 2d minus 2q charge. Now forget this, just forget this, okay, and this is just mirror, and find for point P, suppose this is point P, just find the electric field due to this configuration. That's all. Or more simply, if you are asked to find the electric field or the force experienced by the charge q, suppose you have to find the force on the charge minus q. How can I do that? You have to now find the forces on this charge due to this charge, and this charge, and that's all. You will get the answer. Okay, the forces that is applied by the other charges on this charge, that is electric field multiplied with the charge, amount of the charge. So it is easy. Now another type of problem is like this, that you have this conducting plane okay, you have this conducting plane and you have a charge just above the plane at distance d. Suppose this distance is d and a charge is q. Now you have asked that for this charge q, for the presence of this charge q, what will be the surface charge density on this plane? That is, for this charge there will be a induced charge in the nearby regions of this plane, infinite plane. Now what will be the surface charge density? How can we calculate that? This is one type of, another type of problem. Okay, this is very important type of problem. Again, one more thing can happen, that one more question you can face, that is except a point charge there is a linear charge density. That means there is a line charge, infinite line charge is given, like the line charge density is lambda, infinite line charge positive. Okay, line charge is given, and for this line charge you have to find the similar. For this line charge the induced for this line charge you have to find the surface charge density, induced surface charge density on this conducting plane. So these two are just similar things. So I am first discussing the point charge, for the point charge. So for the point charge, now how can we calculate that? We have, if you remember the previous lecture, that is the lecture on the method of images, you can easily understand that we have calculated the potential for any given point, for any arbitrary point, suppose P, and the expression was what? The expression of potential q divided by root over of, as this is d distance above. Now considering the xyz plane, xyz axis, suppose this is our x axis, the y axis is inside the plane and perpendicular like this. This is our y axis, and z axis is above, like this. Now you can understand that when we consider a coordinate system, we have to always check that this is following whether this is following this rule, I cap cross j cap equals to k cap, and all the others, that is j cos k equals to I and k cross I equals to j. You can easily find that here it is following that I, if you cross from I to j, then that will be upward. If you cross j to k, that is from j to k, you will find the I cap. Okay, so this is right, this is our correct. If we draw this y cap in front direction, that is if the y cap is directed along the towards u, that is above the plane, okay, so that will be not the correct form, because then the I cross j, if we cross, then the I cross j will not be equals to the k cap, that will be the minus k cap, so that is the wrong diagram. Okay, so this is our coordinate system. Now we have calculated, okay, we have calculated that this is the x square plus y square plus z minus d whole square. Now minus, there was minus, so minus q by similar term, that is x square plus y square plus z plus d whole square. So this type of things was there. So the point P, for any point P, the potential is like this. So in that video I have detailedly discussed that how this expression comes. Okay, so now what we have to do, we know the electrostatic boundary conditions. What are these? We know that as this is a conducting plane, infinite conducting plane, we know that if we have a surface charge density like this, if we have a surface with surface charge density, suppose sigma, then the electrostatic boundary condition gives us that E above minus E below is equals to basically the E perpendicular, the perpendicular component, because the parallel components are E1 perpendicular, E1 parallel is equals to E2 parallel. If you don't know how this expression comes, that how the boundary conditions come, then I have a dedicated video. I will give the link of the video in the description box, so you can easily understand the concepts from there. Okay, so the perpendicular component, basically the perpendicular components have a discontinuity near a surface charge surface. Okay, now this the discontinuity amount is sigma over epsilon naught. We know this. Now if we know that E equals to grad phi minus of grad phi, that means minus of dv dn. Okay, now n means the perpendicular, along the perpendicular direction, the derivative is along the perpendicular direction. So here the derivative, as this is z, the perpendicular is z, so here the derivative will be minus of dv above by d z. So this denotes this. Okay, that means E. I have just written E. So there will be the similar expression for E below, and if we generalize that, then we will come that if we common the negative sign, so the negative sign will be in the right hand side, and our expression will be del v del z above minus del v below del z will be equals to minus j minus sigma over epsilon naught. Now for a conductor, we know that inside any conductor the electric field is always 0. So it is an infinite conductor. Okay, it is an infinite conductor. So inside, that means below this conductor, that means inside, this is infinite conductor. So inside this conductor, below this conductor, the electric field is always 0. So here the electric field is 0. That means here the electric field is always 0, because the potential is constant. So the electric field is 0. So this term will vanish, and from here we will get that sigma, the surface charge density, induced surface charge density in this plane will be equals to epsilon naught minus of epsilon naught del v del z, del v above divided by del z. Now we will put this concept here. So this is our expression of v. for any arbitrary point above the plane. So if we derivative this, then we will come the answer. So let us understand that. Calculate the derivative of v with respect to z. Okay, so we know that the derivative d dx of 1 by root x, that means x to the power minus a half, will be what? The minus 1 by 2 x to the power 3 by 2. Similarly, we can use this here. So what will be that? So k minus q by 2 x square plus y square plus z minus d whole square whole to the power 3 by 2 into, as using the chain rule, I can write here that this will be 2 into z minus d minus this minus sign. Okay, now for this type of minus there will be plus, as when we derivative if that for this minus will be cancelled out and this will be plus. Okay, so this will be q 2 z plus d divided by 2 x square plus y square plus z plus d whole square whole to the power 3 by 2. Similarly, okay, so now we want to find the surface charge density sigma on the plane, right, on the conducting plane that is situated at z equals to 0 from the previous figure, as it is the z axis. So this will be at z equals to 0, the xy plane, on the xy plane. So putting z equals to 0 in this expression, I can write, and for getting that we have to use this expression. Okay, so first we have to find the dv dz. So z equals to 0, putting z equals to 0, this will be these two will be cancelled out, and this will be 2qd divided by x square plus y square plus d square whole to the power 3 by 2. Okay, so this is this. Okay, now for what will be the sigma? What will be the sigma? The sigma will be minus epsilon naught. Okay, minus, okay, k means 1 by 4 pi epsilon naught, that is 4 pi epsilon naught. Okay, minus dv dz into epsilon naught, that means epsilon naught. So epsilon naught will be cancelled out, 2 will be cancelled out. So this will be qd divided by 2 pi x square plus y square plus d square whole to the power 3 by 2. Okay, so this is the expression of the surface charge density for the that is induced on the plane, conducting plane. So using this concept, you can easily find that for the line charge density, if we have a line charge density above the plane, then what will be the induced surface charge density on the conducting plane. This type of question. Okay, so I will next in the next videos I will discuss that problem, that is for the line charge density. Okay, for infinite line charge. So I think that you have understood that these are the problems involving the method of images. If you have any doubt, then you can comment below, and if you are new, then subscribe this channel and hit the bell icon to get the notifications of my upcoming videos. So take care of yourself. Thank you for watching.